All right. So what we are going to do is to go over some questions that are relevant to the exam. Okay. Like I mentioned, there are 6 questions on the exam. Okay, and the exam questions are in this format, more or less. Okay. First question is from the sinusoidal response. If I give you a time domain expression for a sinusoidal signal, pretty straightforward, finding the frequency, finding the time, finding the phase, Vmax, and using them in radians, degrees, all that kinds of issues. Then we'll look at a problem. The problem in the exam as well is going to be on frequency domain analysis in operational amplifiers. Okay, so this should give you a pretty good understanding of what is considered a reasonably complicated circuit op-amp with a lot of RL components, and you'll be doing KCL, application of KCL and ideal op-amp principles. Okay, and then we'll do some of the circuit analysis techniques like a node voltage method in frequency domain. Okay, and then there's a problem on transformer specifically, and I don't have any problem giving you a heads up on or a short list of what to expect. Okay, finding a Thevenin's equivalent, looking in from the load side or looking in from the input side. Okay, this is a particularly important problem because you want to make sure that the impedances are matched. The impedance that you find looking from the input side should, to the extent possible, be matched to the impedance looking from the output side. We'll discuss that a little bit more. Then there is power calculations in frequency domain. Okay, complex power. There is average power, there is reactive power, and problems relating to that. My hope is that by talking about these problems, I'll go over examples today. Okay, by going over these examples, my hope is that we cover most of the fundamentals that we should have picked up so far before the exam. Okay, let's see. I prepared a little bit of a cheat sheet for you. Okay, so we'll go over some example problems. Okay, questions, first of all, please. What questions do you have at this point before we get started? Okay, so for the example problems, for the problems that I discussed, that I said we'll go over, the first example problem I chose is from the textbook. Okay, you must have seen many versions of it from the homework. Okay, but if you're using the edition that I am recommending, okay, for this course, which is the 11th edition, then we are looking at the very first problem at the end of the textbook. It's not quite an example, I think, but here is the idea. Vt is given as a cosine formula. Okay, what is the Vm in this case? It's a very quick. The first problem on the exam is straightforward. Okay, so you can participate and give me the answers because it's straightforward here. What is Vm?
40.
40 is Vm. So the exam problem is going to be similar in some sense. How about the frequency? This is the frequency component, right? 100 pi is the frequency component, and that's similar to 2 pi f. Okay, that should give you a value of f to be 50, right? Or whatever, you get the idea, right? And then you can find the value of f in the radians per second. You see, this is, all of this is omega t, right? So you can find the frequency in radians per second. Okay, 100 pi is omega. So you should be able to find uh, the frequency in radians per second. How about this guy? The phase in degrees and phase in radians. Straightforward. Phase in degrees is this guy. Okay, and this guy converted to radians is a degree. Okay, and then you should be able to calculate the period in milliseconds by simply doing 1 over the frequency. Okay, 1 over the frequency. Okay, so watch out on the exam. So the first question is more meant to make you feel comfortable about the exam, and um, and also watch out for a couple of things. Okay, all of this is valid if the input is given in terms of V, volts. Okay, what if there are a few curveballs? What if the voltage is given in VRMS, not in volts directly, but in RMS? How do you go from RMS voltage to V maximum? Okay, so on and so forth. So this guy is not in volts, but in VRMS given. Okay, if it is given in terms of VRMS, pay attention to that kind of nitty-gritty details. Okay, straightforward. And before we get even further into these problems, okay, we're going to look at this example problem. I do want to talk about a couple of resources available to you. Okay, let's see. The first thing is, obviously, if you look at this formula sheet that is available to you, okay, if you open the formula sheet, you should have this handy. You're welcome to have this open on one of your browsers or have it printed for your exam. Number one. Number two is on this page, if you go all the way to the bottom, okay, all the way to the bottom, there is some information about Matlab. You see, the very last thing on the page is information on the Matlab. How you can access Matlab at Sac State. Okay, so if you did not already, there's a little bit of time between now and the final exam. So download Matlab on your laptop, or you can even use Matlab in the cloud or in the servers from Sac State. Okay, how to access that is provided here. What I do is I like to download it on my laptop. But if you're nervous about your laptop crashing during an exam, if you have Matlab and other computationally intensive software, then you can use it in the servers at Sac State. So look at this useful link. Then, again, going back to the Moodle page, the very, very last file is actually this guy. Where is it? Okay, you can open it. Okay, the very, very last page is showing you some examples. This guy showing you some examples. Where did that go? Okay, I may have uploaded the wrong file. Let me see. Easy script. Open in a new tab. That's this guy. Tips on speeding up right here. Yes, it is available. And the right link is available. So if you go further down, this is the example that I talked about yesterday. Okay, when you're solving two equations, V129 plus V2 negative 1 equals to 880 is one equation, and V1 negative 1, V2 17 equals to 240 is the second equation. So two equations, two unknowns. This single page has all that you need to know when you want to write a very simple MATLAB code, okay, to solve this pair of equations, okay, for two unknowns. I already showed you an example yesterday in the office hours on how to solve complex numbers, equations, simultaneous equations in MATLAB. So that's available to you as well. So before we get started on the example problems, I just wanted to mention the resources available at your disposal. Okay. All right. So let's take a look at this problem. And the way this class works is, yes.
For the previous problem, can you go back there for a moment?
Can I go back to this?
No, the previous problem that we did, the VRMS one. Can we go back to the first problem that we did?
So are you still there? Oh boy.
Okay, guys, you guys have to hang in there for a minute. My iPad shut down on me, the Zoom shut down on me, so I'm joining in a minute. So please bear with me for a minute.
It happens.
Yeah, and it's happening too frequently for my liking.
Okay. Let me know when you're able to see my screen.
We can see it.
We can see it now.
Perfect, perfect. Now, who had a question? Somebody wanted me to go back to MATLAB slides?
No, Professor. Can we go to the first problem that we did?
This guy?
No, the VRMS one.
The VRMS one. Yeah, which one? This is the VRMS one, right?
Yeah. So, if it changed to V to VRMS, right? So, how would the values change here?
The only thing that you want to remember is there's a factor of square root of 2. You see, VRMS equals to Vmax over square root of 2. So if everything is given in terms of VRMS, you just want to account for that extra square root of 2. You may have to divide it or multiply it. Okay. Okay, if everything is given in terms of VRMS, that means the actual answer that you're looking for, you can get it by multiplying by square root of 2.
Okay, so for this problem, the VM would be 40 times square root 2, and then rest of the thing would be the same, I guess.
Nothing else changes, correct? And
Yeah,
the other thing is, yes, and that brings me to an important suggestion about the exam, which is, let's see, let me make sure this is recording. Okay, the suggestion for the exam is if you're reasonably confident, then do not check your answer. Okay, it incurs some loss. So unless you are about 30%, I don't know, there's a small loss that you could incur if you're not, if you're checking the answer. Okay. All right. So let's see. Let's look at other questions, please. Thank you for that question. What other questions do you have, please? Okay, can we look at this? How do you guys want to start solving this problem? The problem is this: you're given an operational amplifier problem, and they say that this is an ideal op-amp. Okay, and the assumptions about ideal op-amp can help signify our life. Okay, so that's the first piece of information given, that this is an ideal op-amp. Okay, and this voltage VG is given to be some sinusoidal waveform. Okay, and then the op-amp is obviously connected in a negative feedback configuration with a bunch of resistors. Let me see. Let me highlight using this guy. With a bunch of resistors. Okay, and then it seems there is one capacitance here. Okay, how would you go about solving this problem? Any directions? KCL, right? So where would you apply KCL?
The nodes that are just behind the op-amp.
Correct. We call, there are two nodes here that are of interest. We'll call one as negative Vn, okay? The negative node, because it's connected to the negative terminal. And then we'll call this node as positive Vp, okay? Sure. Now, let's see, first things first, that's correct. So we can apply KCL in a couple of different places and then massage the equations, okay? So let's try to apply KCL. So solution. KCL at node Vn, okay? How would you apply KCL at node Vn? What are the different components that factor into the equation at Vn? Right? It seems there are four currents. There's one current going down this branch. There's another current going down this branch. So it seems there are four currents that are leaving this node. Okay, so KCL says if I add up all the four currents, then that should sum to zero. Okay, so let's look at the current leaving that node first. Okay, that would be Vn minus 0 by 160 ohms, 160 kilo ohms. Okay, for a minute, I'm simply going to erase all of this. Okay, except maybe this guy. Okay, okay, let's bring this up. Okay, so KCL at node Vn, we are interested in looking at the different currents. The current going left is voltage at Vn minus voltage at this guy, which is 0, divided by 160 kilo ohms, plus the current going into the negative terminal, IN. Okay, IN plus the current going through the capacitance, Okay, what is the current going through the capacitance? Well, the current going through the capacitance would be the voltage there, which is Vn, right? Minus the voltage here, which is the output node V0, okay, by Zc. So that's the advantage of writing in frequency domain, capital Vn, capital In, and all of that. You don't have to worry about j omega anymore. You can simply pretend like the capacitance is pretty similar to a resistor. Then what else? What other branch do we have to take into account? What other branch do we have to take into account? Guys, if you're not going to participate, we will not be able to make any progress. So we have taken into account 3 branches, right? The 3 branches are one going to the left, okay? One going into the op-amp, IN.
The 200K ohm.
The current through
On
the
the far
200
right.
kilo ohm resistance, correct, thank you. So what would that be?
LP,
Vn.
Go ahead.
Oh yeah. Vn minus V naught divided by 200K.
200K, thank you. I appreciate it if you're participating. That way, I know how the pace is doing, okay? If we need to slow down or speed up, your feedback is important. So this is the first equation that we have set up by writing KCL at Vn. What is the easiest simplification? What is the easiest thing we can do right away?
Plug in the variable if we have it.
Plug in the variables, sure, but noticing that this is an ideal op-amp, okay? One of the main rules of ideal op-amp is the current going in to either of these terminals, okay? The current going into either of these terminals is 0, okay? Meaning that IP is 0 also means that IN is 0. So one of the first things we can do is to throw this guy away. This is 0 because ideal op-amp. Okay, and like you mentioned, now we can plug in the variables. ZC, we know ZC, how to calculate ZC, negative J over omega C. Okay, we can plug in the value of omega to be 100K, and then C to be 0.1 nanofarads. So omega is, you plug that in, you'll get a value of negative J 100,000 ohms, 100K ohms. So this guy was 0.1 nanofarads or whatever value was given. Okay, so this is, we can now plug these numbers in and of course, solve this equation a little bit more. Let me factor out V in first. From the first term, I'm going to see a 160 kilo ohm, okay, plus 1 over J 100,000 ohms. That's because of this, okay? That's here. And this Vn is over here, right? We will account for V0 later on, but we have already taken care of this one in this term here, okay? Plus, there is a factor of 200K Vn. So plus 1 over 200k ohms. Okay, and let's not forget the V0 as well, plus V0 times negative of 1 over negative J 100,000. So let's not forget this has a negative term associated with it. Minus, there's this, there's that minus, okay? There's a minus term, that's where this minus is coming from. And then a 200 kilo ohm, minus 1 over 200,000 ohms. Okay, so all we have done is to set up a KCL at node Vn, and the rest is algebraic simplification. So KCL told us that all of this equals to 0. Okay, we can simplify this. We can simplify this and then get an expression that looks, so there's only two variables here. There's Vn and there's V0. Okay, so you simplify this, you're going to get something that looks like V0 equals to Vn 9 plus J8 by 9 4 plus J8. Okay, everybody with me so far? There's nothing from this step to this step, there's not a whole lot. It's just manipulating algebraically and making sure that you account for all these numbers. Okay. Questions, please. So this is as far as we can get by writing a KCL at node Vn. Okay. So let's try to do the same thing at node Vp as well.
Excuse me, sir. Mind if you scroll up a bit? I want to take a look just a little more. Just a little more.
Of course. Is that good?
Yes. Okay, thank you, sir.
Of course, yeah. And this notes is going to be available to you on Google Drive. So
Oh, okay.
you can
I
can
thought
copy all of
I
this.
heard you. Yeah.
Go ahead, say that again.
Sorry, I thought I heard you say these won't be available
Yeah,
before
the
exam.
recording won't be, but the notes will be.
I see. Thank you, sir.
Yeah, I should have clarified that. Okay, so far what we have done is to set up KCL at node Vn. Okay, we did that. So let's do the exact same thing for Vp as well. Okay, so somebody's got to tell me the equations for Vp.
VG plus
Minus
minus, yeah.
VP over 80K.
Over
Oh, I guess in this case, since you drew it that way, VP minus VG over 80K.
Thank you.
And then that one's going to be facing down. So VP over 80K plus, yeah.
We know IP is 0, the current going in IP is 0. So we can massage this equation. Okay, this is straightforward. What we will see is VP equals to VG times 80K over 20K plus 80K. Okay, the idea is forget about this guy if you forget about that for a minute. Okay, you can see that VG is a voltage division. Something is wrong here. Something is wrong. One of these is 20K. This guy is 20K. So sorry about that. So this is 20K. So you would see a 20K over here. Okay, and the rest is the same then. Okay, so two equations. This is the second equation that I would get. Okay, taking these two equations, what is the next step? What do you think would be the next step?
Look at the KCL for the other node.
Look at the KCL for the other node. Okay, let me copy this and paste it over here. So there is only two nodes. Okay, there's no point doing a KCL for this node because it's the output node and it's just two currents flowing out. Okay, there's no insight that we can gain by looking at that KCL over there.
Oh, I didn't realize we had to resolve for Vn.
Yes, perfect. We already did KCL at Vn. Okay, this is KCL at Vp. Now we apply two op-amp rules so far. Okay, the two op-amp rules that we applied so far are that IN equals to 0 and IP equals to 0. What other ideal op-amp rule can we apply here to make our life, well, to take us forward? Does that ring a bell? Virtual short. What does virtual short mean?
So VP is equal to Vn.
VP equals to Vn, correct. VP equals to Vn. So now what we can do is in place of this VP, we can plug in Vn, or in place of Vn, we can plug in VP. Okay, so V output equals to VP times 9 plus J8 by 4 plus J8. Okay, and in place of VP, I'm going to plug this in. Okay, that's simply V output equals to VG into, all of that is simply 0.8, 0.8. Okay, 80 by 100. Okay, 4 by 5 into this complex number, 9 plus J8 by 4 plus J8. You see, now our problem is getting simpler and simpler. If only we knew the value of VG, the rest is all known. But guess what? We already know the value of VG. Do we? Two angles 0 degrees, right? Two angles 0 degrees, capital VG. So simply plug that in, 2 angle VG, angle 0, okay, times this number, 4 by 5 times 9 plus J8 by 4 plus J8. Okay, all of this is going to come out to VO equals to 2.154 angle negative 21.80 degrees. Okay, from here we should be able to write the V0 of t in terms of the cosine form. Okay, so we should be able to do all of this in Matlab as well. Try doing all of these equations. Questions about this, please? So the simple solution here is to set up KCL at two nodes, IN equals to 0, IP equals to 0, VP equals to VN, okay? And the rest is mathematical simplification. Questions? Okay, if you don't have questions, maybe I have questions for you. Take a look at this guy. Let me see if I can highlight using, oops, this color. Take a look at the input voltage. Is that a constant DC voltage, or is that a time varying signal?
Time varying?
It's a time varying signal. And if it's a time varying signal, I just showed you how to work this problem. But what if instead of a time varying signal, I gave you VG to be a constant 5 volts or something else, some other signal that's not time varying? What changes do you think would happen in this problem if the input voltage is not time varying, but rather a constant DC value?
You just wouldn't have imaginary numbers in your answer.
There would not be any imaginary numbers in the answer. Not just that. Correct.
Well, I
That's
guess while
correct.
working
So
it out as well.
while working it out as well. And what do you think happens to the capacitor?
Becomes an open circuit.
It becomes an open circuit. So if you have a constant DC voltage, your problem is going to be further simplified in the sense that now you have a circuit that has just resistors and a constant DC value. This capacitance is not present. Okay. All right. I thought it would be best for you to think about it now rather than having to think about it freshly during the exam. So that's a bit of a sneak peek into the kind of the kind of spin that I could put on the exam problem that we just discussed so far. Okay, so what I sense is that you're all very comfortable with these techniques. So we're going to take it a little quicker here. Okay, look at this problem. So the other problem on the exam, so we looked at two problems. The first problem is simply the sinusoidal signal. The second problem is op-amp in frequency domain. Now we are interested in applying this node voltage method in frequency domain to this circuit. Okay, and let me also mention for the 50th time today that you can use Matlab in the exam. Okay, so V1 is given to be some 10 cosine 5000 t plus some angle. V2 on the right hand side is given, okay, to be some 8 sine 5000 t. You're asked to find out the voltage across this resistance in time domain. Any suggestions? And then the suggestion is that you should use the node voltage method. Did you see this kind of problem in the homework at all?
Yes.
Okay, so let's see if we can work on work on this. Where do you want to start?
GCL from V naught.
Can start from V. Did you say V naught?
Yes.
Okay, correct. We'll start from V naught, but before doing that, let's convert this into frequency domain, which simply means we are going to convert J omega L in place of this guy and minus J by omega C in place of this guy. Okay. What's the omega here? Omega is 5,000. Okay. If you convert this to 5,000, anybody can give me the numbers here really quickly? J omega is J times 5,000 times 0.4 milli
2J.
2J. Thank you. How about this guy?
-4.
Negative 4J. Thank you. So first things first, we converted this to frequency domain. Okay. And then the first thing, the first step in doing the nodal analysis is to pick one node to be the ground node. Let's pick this node, the one at the bottom, to be the ground node, and the other node to be just some V1. Doesn't matter. Okay. V1 node voltage method. Okay, so one is VG1. If you were to convert this VG1 into frequency domain, into polar form, it's going to be 10 angle 53.13, right? And if you convert this into polar form, owing to the fact that it is in a sinusoid form, you would get 8 angle negative 90 degrees. Okay, and you can of course convert it to rectangular form, 6 plus J8, and this would be 0 minus J8. Okay, VG1 and VG2 in their polar and rectangular forms. Okay, so far so good. Now the next thing we are going to do is to look at the node V. Let's call this node VO. Okay, let's call that node VO, and then set up the KCL at node VO, node voltage method. Okay. Node V0, there are 3 currents flowing out. Okay, the 3 currents. Could you help me with the equation here really quickly?
V out over VG1 over J2 minus, yeah.
Negative J2. J2 is
Yeah,
correct.
just J2.
Okay, plus
Plus V out plus VG2 over negative J4. And then V out over 6 ohms equals 0.
thank you. Correct. So you you separate out the terms, V0 term, and then you'd get everything else is known, right? So V0 is the only unknown. We know VG1, we know VG2, the only unknown here. So we don't need to set up any more equations. That's the only unknown. So you can, it's a matter of massaging this equation. V0 would come out to be 12 plus J0 volts. Okay, or 12 angle 0 volts. And that's it, there is to doing this. Okay, so if you had a different kind, if you had a different kind of a circuit, you would, with more than one unknowns, okay, then you would have to set up two equations. So for example, if this circuit looked something like this, okay, with an additional node V1, then you would have to write KCL at this node as well. And then there are two equations, two unknowns. That would be fun. Okay, but for now, you get the idea. All we have done is to apply the node voltage method in the frequency domain by writing KCL. Okay, questions, please. Questions. What questions do you have? Okay, let's look at the other problem then. Anything in the chat? Okay, let's look at the other problem. The problem is in transformers. Okay, particularly you're asked to find the Thevenin's equivalent circuit or the Thevenin's impedance. What is the Thevenin's impedance? Looking into the terminals here. Okay. How do you find the Thevenin's equivalent impedance? Z Thevenin looking into terminal CD. This is a linear transformer. There is some impedance. There is some impedance associated with the primary and secondary coils. Okay. Then there is this mutual inductance, J50 ohms. Okay. And there is this impedance here, 15 ohm resistance in the primary and 15 ohm resistance in the secondary. First of all, what is Z11 in this case? What is Z11 in this transformer?
15 plus J20.
15 plus J20. In Z22?
30 plus J200.
J200. All right. And what's the omega? Is omega given at all? VRMS. So this guy is, let's pay attention, this guy is VRMS. Let me not forget that. V Thevenin, J omega is, well, omega is not given. Let's see if we can solve this without having to explicitly need omega. Okay. What is J omega M? What term does that correspond to?
J50.
J50, thank you. J omega M corresponds to J50 terms. So now we have, can we calculate ZR from here? Z reflected from here. Okay. Or in other words, the idea is we are interested in looking at the impedance into the terminals of C and D. Okay. Therefore, the reflected impedance is going to be coming in from the other side, Z11 side. Okay. So the impedance reflected from the first, from the primary side is going to be omega M by mod Z11, okay, whole squared into the complex conjugate of Z11. Okay, let's see. If I go back here and look at this transformer somewhere in here, okay, we should have seen that formula, okay, somewhere, okay. Here you see there's a formula for I2, okay, and then reflected impedance, so on and so forth, right here, there. Okay, if you're interested in calculating the impedance that's reflected from the secondary side into the primary side, then you have this formula, omega m by Z22 whole squared times the complex conjugate of Z22. But now you're interested in calculating the impedance reflected from the primary side into the secondary. So in place of Z22, you plug in Z11. Okay, let's see. Z11, and that's all there is to it. And let me see if I can go back here. And maybe it is on the formula somewhere in here. Chapter 9, 10. Well, it's not here. You probably can add it. Okay, so you can plug this in. You can plug in, you have a value for omega m to be 50. Okay, you can find out the mod Z11. The modulus of that is square root of 15 squared plus 20 squared. Okay, so you can get a number for it, whatever that is. 400 plus 225, 625. So you get the idea. Okay, from there you can calculate ZR to be 60 minus J80 ohms. Okay, once you have the Z reflected, then Z Thevenin is Z22 plus Z reflected. Okay, or in other words, here is the deal. When you're looking in to the terminals CD, okay, you would see this guy plus this guy plus an impedance that is reflected from here. Okay, so this sum of those three is 30 plus J200 plus 60 minus J80. So how much ever that comes out to be. So Z Thevenin is 90 plus J120. Make sense? Questions, please. Okay. The next problem, here's what I'm going to do. I'm simply going to give you a hint because I don't want to belabor the point. Okay. You're given a circuit that looks like this. Okay. There is a current source, IG, with some Vm, omega, and phi. Okay. So IG equals to 4 angle 0 degrees. Theta I is 0 degrees. Okay, theta I is 0 degrees. Okay, you're asked to calculate the average power. Okay, the average power in watts. It is simply P. And then the reactive power, Q, in VAR. Okay, you can simply use these formulas. Vm Im by 2 and cos theta minus theta v minus theta I will give you the average power. Okay, and Q in volt ampere reactive. Okay, now the question is, let me make this a bit more clear. Average power delivered or absorbed, and the reactive power delivered or absorbed by the current source Ig. That is what you're asked to find out. Okay, so I guess how would you go about doing this? We have theta I, right? Theta I is that guy. And we have Im. Okay, we have Im and theta I. But I guess to use the formula, we need more terms. We need this guy. Theta V is not known and Vm is not known. How would you go about finding Vm angle theta V? Or in other words, how would you find the voltage across this current source?
Thevenize the circuit.
Say that again.
Thevenize the circuit.
Yes, yes. So we can we notice that this is a bunch of resistors, capacitor, and an inductor. So what we can do is simply, if we were to find one impedance, Z equivalent, okay, that is being driven by this Ig, okay, then what we can do is Vg is Ig times Z equivalent. Okay, so you're right. We can simplify all of this into a single impedance. Okay, first of all, we have two impedances in series that is in parallel with this guy, which is in series with this. So we can simply apply series parallel simplification of impedances to find an equivalent ZEQ. Okay, or in other words, you can write this as ZC or ZL. You can write this as ZC, and then you can simplify series parallel. When you do that, you'd get a Z equivalent of 1581.1388 angle negative 18.43 degrees. Okay, so this is Z equivalent. So in order to find Vg, all you got to do is to multiply the two. Okay, so you can do Vg equals to Ig times Z equivalent. Okay, then you would get an expression for Vg to be 6 minus J2 volts. Okay, 6 minus J2 volts. Okay, so what you can do is to find the average power. Okay, this is of course you can write this in 6. If you write this in polar form, it's going to be 6.3246 angle negative 18.43. Okay, and angle negative 18.43 degrees. Okay, now what you can do is you have your Vm now. Okay, your Vm and your theta V. Now you have everything you need in this equation. There is that Vm, there is this Im, which is given, theta V and theta I. It's a matter of plugging in. into the cosine and sine trigonometric functions. Questions, please. Okay, so that should do it for for both 5 and 6 problems. Okay, so now you have a sense of not only what to expect on the exam, but also a very vague picture of the kind of skill set that this exam calls for, and the time, okay, the time that it takes. Be prepared to go back and forth between these calculations. Let me do this. This is what I'm going to do. I'm going to let the notes back up. Okay, like I mentioned, I did not clarify it earlier. The recording will not be available to you, okay, until after the exam. But what will be available is the notes. This notes is all backed up to Google Drive, so you should be able to, let's see, go on Moodle, wherever that Moodle site is. Let's see, Moodle, PW, Moodle. Okay, let's see if I can go to the Moodle site. Engineering 117 and Google Drive notes. Okay, somewhere in here. I wonder why it's not. Okay, let me try this one more time. Well, it will be uploaded. I wonder why it's not.
Professor, I can see it on Moodle.
Oh, you can see it on Google Drive, right? And from Moodle.
Yeah, I can see it. It's
okay. Yeah, perfect. So that's good. So you have that's more than anybody can ask for. Okay, solutions, kind of problems. The only caveat here that I would say is these are not the exact problems, obviously. I will trust that you are going to use this as just a starting point. Okay, do not blame me if you go into the exam just expecting these and you find yourself lacking 1 or 2 skills that are necessary to complete the exam. Okay, so use this as a starting point. Use this as just an indication of the kind of topics for the exam, and that's about it. Other questions, please?
Quick question.
Yes.
So, first of all, is the exam going to be open note or no?
Yeah, you can, yes. Yes. There's no way for me to impose, a closed notes policy. Okay.
Okay. And also, so is the exam going to be like that we're like, is it like homework that we just go into the Moodle and enter like our answers into the boxes, or will we just be given a set of problems and then we will write down our answers on the note, on a piece of paper and then upload it?
It'll be pretty similar to the homework.
Okay. All right. And also, would will you have any office hour tomorrow before the exam happens, or?
Sure. I don't plan on holding office hours, but if you have questions, you're welcome to email me. I will make an effort to make myself available before the exam.
Okay, thank you.
Okay. Yep.
Yep, that's it for me.
Yes. Other questions?
Professor.
Yes.
So for the power problems, say a value is positive. So we say that the positive value means that the power is absorbed or that is
Yes.
delivered.
Absorbed.
So positive
Positive
means
is absorbing
absorbed
and
and
negative is delivering.
negative is delivered. Okay.
Yeah. Other questions? That's a good question. So if you want, you can look at the practice quizzes. And what do you guys think? Do you guys want to look at chapter 10 tomorrow, or do you want to work on some problems for tomorrow's class time? I mean, on your own. We don't have to meet tomorrow if we don't have to, unless you want to. So let me do this. Let me stop recording here.